Welcome back to the deep dive. It is quite late.
Too late, maybe.
Yeah, the coffee is definitely cold by now.
Mine is basically sludge at this point.
Right. And honestly, it's probably doing more harm than good right now anyway.
Yeah.
But here we are, all staring at our screens.
As usual.
Exactly.
Who?
But tonight, for once, you and I are not trying to vertically center a div.
Thank goodness for that.
And we aren't debugging some obscure race condition that only happens on Tuesdays either.
No, we are tackling something that usually sits in the too hard basket for a lot of us.
The elephant in the server room.
Machine learning.
Exactly. We're talking about the actual bare metal mechanics of machine learning.
Right, and I want to be clear, we don't mean the high-level marketing fluff here.
No, definitely not.
Yep.
Or those sci-fi nightmare scenarios you see on social media.
We have a stack of papers and notes here that strip all that magic away.
Because if you are listening to this right now, you are likely an engineer.
You know how to build systems.
You know logic. But this requires a totally different part of the brain.
It really does. It's a fundamental shift from being an architect of rules to being a curator of experience.
That is exactly the mission for tonight's deep dive.
Demystifying the black box.
We are going to move from that feeling of its magic to understanding the specific loop that makes it tick.
The predict, compare, adjust loop.
Right, the loop that powers everything from a basic linear regression script to the massive LLMs we use every single day.
And the best part is that it is not actually magic at all.
No.
No, it is just statistics at scale.
So let's start with the friction, the core conflict.
Okay.
Because as a developer, when I write code, I am essentially a dictator.
You set the rules.
Yeah, if this user is logged in, then show the dashboard. Else, throw a 403 error. It is entirely explicit.
You are in control of every single branch of that logic.
I am. I encode my exact understanding of the problem into these rigid step-by-step rules. I'm telling the machine exactly how the world works.
Which is comfortable. But the sources we're looking at today describe machine learning as a massive epistemological shift.
Epistemological shift. That sounds incredibly heavy. What does that actually mean for the person sitting there typing at the keyboard?
It sounds super philosophical, but it is deeply practical. Think about the house price problem.
Ah, yes, the hello world of ML.
Exactly. Imagine you have to write a program to value a house. In the traditional dictator mindset, what do?
Well, I would probably go find a real estate agent. I'd sit them down, buy them a coffee, and just ask, how do you do it?
And what would they say?
It would say something like, add $50,000 for an extra bedroom, or subtract $10,000 if it is near a busy highway.
Right.
Then I would go back to my IDE and write a massive function with 1,000 if statements.
And that works. For a bit.
Until it doesn't. Because what if a house has 5 bedrooms, but is located in a literal swamp?
Yeah, the rules break down.
Or what if near a highway increases the value in a commercial zone because of visibility, but decreases it in a residential zone because of noise?
My if statements would just start colliding.
The complexity explodes. I am suddenly writing exceptions for my exceptions.
Precisely. You hit a complexity ceiling. You literally cannot manually encode the millions of subtle interactions that exist in the real world.
It's too much.
So the epistemological shift is this: you stop writing the rules.
I stopped trying to explain the world to the computer.
Yes.
I just shut up and let the data talk.
You curate the data. You gather 100,000 records of house sales.
Inputs like size, location, bedrooms.
And the output, the actual price it sold for. You feed that entire pile into the machine and say, you figure out the function that maps these inputs to this output.
So I am not writing the logic anymore.
Not the core logic, no.
I am defining the architecture that contains the logic, and the machine fills in the blanks.
That is a brilliant way to put it. The data encodes the rules, and the machine extracts them.
That makes a lot of sense.
And often it finds rules a human would never even articulate.
Like what?
Well, maybe it finds that houses built in 1982 in a specific zip code are undervalued by exactly 3%, but only if they have a brick facade.
Wow. No human is coding that rule. It is way too subtle.
Exactly. But the data shows it, so the machine finds it.
Okay, but that implies the machine has a way to find that rule. And this is where I think engineers get really hung up.
How so?
We say the machine learns, but that completely anthropomorphizes it. It's not sitting there pondering a housing market with a pipe in its hand.
No, definitely not. It is doing math. Very specific, very repetitive math.
So let's open up the hood. The sources talk about the training loop. This seems to be the universal engine, whether we are predicting prices or generating poetry.
It is the absolute heartbeat of all modern AI, and it is surprisingly simple.
It is a three-step cycle, right? Predict, compare, adjust.
That's the loop.
The sources use this blindfolded darks analogy. I want to drill into this because it really clicked for me when reading the material.
It is a classic analogy. Imagine you were standing in a room, entirely blindfolded. You have a dart in your hand.
Okay.
You need to hit a bullseye on the far wall, but you have absolutely no idea where the board is.
So step one is predict. I just throw the dart.
And since you know nothing about the room, where does it go?
Probably straight into the drywall. Or my foot. It is totally random noise.
Exactly. In ML terms, your model is initialized with random parameters. It is just guessing blindly. Now we hit step 2.
Compare.
Yes.
This is where the supervisor comes in, right? Supervised learning.
Yes, you have a supervisor standing next to you who can actually see the board.
But they don't tell me where the board is.
No, they just yell out the error. They say, you were 5 feet too far to the left and 2 feet too high.
That measurement, the exact distance between my dart and the bullseye, that is the loss.
That is the loss function. It is a mathematical score of exactly how wrong you are.
And the goal of the entire game is to get that number to 0.
That is the only goal.
Okay, so I know I'm wrong. Step 3 is adjust. I shift my stance. I change my arm angle a little bit.
You tweak your internal parameters and
And
then
hit row again.
predict. And the supervisor yells again, compare! Okay, now you are only 4 feet to the left.
And I adjust again. And we do this loop a million times.
Eventually, your internal parameters, your stance, your grip, your angle are tuned so perfectly that you hit the bullseye every single time.
Even though I still can't see the board.
You don't know what a dartboard is, but you have learned a mathematical representation of how to hit it perfectly.
That distinction is so crucial. It hasn't learned what the task is. It has learned how to minimize the error in the task.
Spot on. The knowledge is just a set of parameters tuned to minimize loss.
Let's ground this in actual code then. Because shifting my stance is a nice metaphor, but in a computer, we are changing numbers.
We are.
The sources bring up linear regression as the simplest mental model for this.
Linear regression is basically the great-grandfather of neural networks.
Now, I haven't done stats since college, but that is just y equals mx plus b, right? Fitting a line to a scatter plot.
It is, but let's look at it through the machine learning lens. You have an input, like house size, and an output, like price.
And I want a line that cuts right through the middle of the data.
Exactly. The equation is price equals weight times size plus bias.
Okay, let's define those terms for the devs listening. Weights and biases. We hear these words constantly in AI news.
Think of them as the knobs on a mixing board. The weight is the importance of the input.
So if the weight for size is really high, then a tiny change in size creates a massive change in price.
Right. And if the weight is 0, the size doesn't matter at all to the final price.
And the bias.
The bias is the offset. It is the activation threshold. Even if a house has 0 square footage, it might still have a base value just for the land itself.
That base value is the bias.
Yes. It allows the line to shift up and down without changing the actual angle of the slope.
So when we start our blindfolded darts game with this,
The machine picks a random weight and a random bias. It draws a completely random line.
the line is terrible. The error is huge.
And the adjust phase kicks in.
This is where the magic really happens, right?
Yes. We use something called gradient descent.
Gradient descent.
Imagine you are standing on top of a mountain at night. Thick fog everywhere. You want to get down to the valley floor, but you can't see the bottom. What do?
I feel the ground with my feet. I find which way is sloping downward, and I take a step in that direction.
Exactly. The mountain is the error. High up is high error. The valley is low error.
So the math calculates the slope of the ground, the gradient.
And it tells the computer, nudge the way up by 0.01, nudge the bias down by 0.05.
And if I take enough steps downhill, eventually I am standing at the bottom.
You have minimized the error. That is a fully trained model.
It seems almost too trivial when you talk about a single straight line.
Mm-hmm.
But the expert notes here make a really huge claim.
Let's hear it.
They say that massive models, like GPT-4 or Claude, are essentially doing this exact same thing.
It sounds totally reductive, but yes. A linear regression has 2 parameters to tune. A modern LLM has trillions.
Trillions of knobs.
Instead of fitting a straight line in 2-dimensional space, it is fitting a hyper-complex shape in billion-dimensional space.
But the loop itself.
Predict, calculate loss, nudge parameters via gradient descent. It is absolutely identical.
That scale is just hard to wrap your head around.
It is staggering.
But there is another distinction in the sources that I think helps clarify what these massive models are actually doing.
The output types.
Yeah. We talked about house prices, which is a continuous number on a sliding scale. That is regression.
But an LLM doesn't predict a continuous number. It predicts words.
Right. This is the big difference between regression and classification.
Regression asks how much. Classification asks which one.
Is this email spam or not spam? That is binary classification.
Is this a picture of a dog, a cat, or a bird? That is multi-classification.
And the surprise for me in these notes was finding out that LLMs are just classifiers.
That trips a lot of people up.
I always thought of them as generators.
Yeah.
I type a prompt, it creates an answer out of thin air.
We experience them as creators, but mechanically under the hood, they are classifiers.
Let's walk through that. What is actually happening?
You give the model a sentence. The cat sat on the...
And it has to predict the next word.
Right. But it doesn't just pull a word out of the ether. It has a statting list of every word in its vocabulary. Let's say 50,000 words.
Okay.
It treats Matt as category A, hat as category B, space station as category C.
Wait, so it calculates a probability score for every single category in that giant list.
Yes, it calculates probabilities across the entire vocabulary.
So it is saying, I am 90% sure the next category is Matt, 5% sure it is floor, and 0.0001% sure it is space station.
Exactly. It is a massive classification problem repeated over and over and over again.
And the error measurement changes for this, right?
We use something called cross-entropy loss instead of just measuring physical distance like in regression. But the primary goal is exactly the same.
Minimize the surprise.
Right.
Maximize the probability of the correct category coming next.
You got it.
That frames it completely differently for me. It is not writing. It is sorting. It is categorized prediction at an unimaginably massive scale.
Which completely explains why they hallucinate, doesn't it?
Oh, have that.
Because if the probability of a true fact and a total fiction are statistically similar in the training data, the model might just flip a coin between the two.
It doesn't know truth.
Not at all. It only knows the mathematical likelihood of this token following that token.
That is a very sobering thought.
It's important to keep in mind.
Okay, so we have the engine, we have the fuel, which is the data, but surely it can't be this seamless. There has to be a trap.
Oh, there is a massive trap.
Yeah.
And pretty much every junior ML engineer falls into it at least once. It is called overfitting.
Overfitting. The sources use a high school analogy here that honestly gave me flashbacks. The memorizing student.
We all knew that kid in school. Imagine two students studying for a big history exam. Student A tries to actually understand the causes of the war.
The economics, the politics, the context.
They are learning the general patterns.
That is the goal.
Hmm.
True generalization.
Right. Now look at student B. Student B manages to steal a copy of last year's exam. They don't study history at all. They just memorize the answer key.
Question 1 is C. Question 2 is A.
Exactly. If you give them that specific exam, student B gets 100%.
They look like an absolute genius. Their loss is 0.
But what happens when they walk into the real exam and the teacher has simply rephrased the questions?
They crash and burn completely.
That is overfitting. Your model has memorized the noise in the specific training data instead of learning the actual underlying signal.
Visually, the notes describe this as the squiggly line problem.
That's a great visual.
If I have data points scattered in a general trend, I could draw a straight line that misses a few but captures the overall direction.
The general trend?
Or I could draw a crazy super squiggly line that connects every single dot perfectly.
The squiggly line has 0 error on the data it has already seen.
But if you add a brand new data point,
The squiggly line is likely miles away from it because it was reacting to the noise of the old data, not the actual trend.
so as engineers building these systems, how do we stop the machine from cheating like student B? We wanted to learn the concept, not the answer key.
We treat the data like a locked vault. You never, ever let the model see all the data during training.
The train test split.
It is the absolute golden rule of machine learning. You take your data and you split it, usually 80% for training, 20% for testing.
You let the model learn on the 80%.
It can fail, adjust, retry, whatever it needs to do. But that remaining 20%, that is the held out set. The model never sees it.
It is the final exam.
Exactly. Once you think the model is completely ready, you run it on the test set.
And if you got 99% accuracy on the training data, but only 50% on the test data,
You know, it's just memorizing. You have overfit the model.
Now, I have seen references to a validation set too. Is that different from the test set?
Yeah, that is for the pros. It is a three-way split. Train, validate, test.
How does that work?
Think of the validation set as mock exams leading up to the final. You use it to tune the hyperparameters like the learning rate or the overall model size while you are still training.
But the actual test set remains completely untouched.
Sacred. You only unlock it once, at the very end of the process. If you use the test set to make decisions during training, you are effectively letting the student peek at the final exam questions.
You invalidate your own results.
Exactly. It is strict, but it makes total sense.
Yeah.
Without that rigorous separation, you have absolutely no idea if your system actually works or if it is just a giant lookup table.
And in the real world, generalization is the only thing that matters.
The only thing.
I want to zoom out for a second here, because as we talk through all of this, linear regression, gradient descent, perceptrons, these are not new ideas at all.
Not even close.
Gauss was doing regression in the 1800s. The original perceptron paper was published in, what, 1958?
Yeah, the core math has been sitting on the shelf for decades.
So why now? Why are we having this deep dive today in the 2020s and not back in 1995? What was the catalyst?
It essentially comes down to two major bottlenecks that finally burst at the exact same time: data and compute.
Let's break those down. Data seems pretty obvious. The internet happened.
Right. In the 90s, if you wanted to train a model to recognize a cat, where do you get 100,000 labeled photos of cats?
You would have to go out with a camera, take photos, scan them, and manually type cat into a database for months.
It was physically impossible.
Enter ImageNet, Flickr, social media.
Suddenly, humanity voluntarily created the largest labeled dataset in the history of the world. We provided the textbooks for the machines.
But even with all that data, we still had a hardware problem.
The compute side. This is actually my favorite historical accident in all of tech.
Okay, let's hear it.
Neural networks require a very specific type of math: matrix multiplication.
Taking a grid of numbers and multiplying it by another grid of numbers.
Over and over, millions of times continuously.
And standard CPUs, like the Intel chip in a regular laptop, are not designed for that.
Not really. A CPU is like a Ferrari. It is incredibly fast at doing one very complex thing at a time: logic, branching, sequential processing.
But a neural net needs to do a million simple things all at once.
It is not a Ferrari task. It is a task for 1,000 ants moving dirt simultaneously.
Parallel processing.
Right. And it turns out there was already an entire multi-billion-dollar industry completely obsessed with parallel matrix multiplication.
Gamers.
Video games. Think about rendering a modern game. You have a screen with 2 million pixels. For every single pixel, 60 times a second, you have to calculate lighting, texture, geometry.
That is a massive matrix operation.
A completely massive one.
So the GPU, the graphics processing unit, was accidentally the absolute perfect AI chip.
Unironically, yes. Around 2012, researchers realized, wait, if we put this neural net on an NVIDIA graphics card instead of a standard CPU, it runs 100 times faster.
That was the big bang.
We were just waiting for gamers to fund the hardware research and development that would eventually power the entire AI revolution.
That is a fantastic bit of tech history. So let's bring this all back to you, the listener. We have covered the epistemological shift, moving from hard rules to data.
We covered the engine: predict, compare, adjust.
We looked at the math under the hood: weights, biases, and gradients. And we covered the safeguards: train and test splits.
That is the full stack.
There is one last concept in the notes regarding feature engineering. I think this is where the role of the software engineer is really heading next.
Yeah, in the old days, like a decade ago, if you wanted to detect a face in an image, you, the engineer, had to manually define what a face actually is.
You would write explicit code to look for circular shapes near the top, or specific distances between dark spots.
You were manually engineering the features. It was an art form. You had to know the domain perfectly.
But deep learning automated that entire process.
The deep learning refers to layers of neurons. The first layer just learns basic edges.
The next layer combines those edges to learn shapes.
And the next layer combines shapes to learn eyes or noses.
So the model is doing its own feature engineering.
Exactly. Your job as an engineer is not to tell the model what to look for anymore. It is to build the pipeline, clean the data, and set up the architecture so the model can learn what to look for on its own.
You are moving way up the abstraction ladder.
You aren't the bricklayer anymore. You are the site manager.
Or the curriculum designer.
That's a great way to look at it.
Which leads to a thought I have been mulling over since reading these sources. If the curriculum is just data,
Right.
and the teacher is just a mathematical feedback loop.
Yes.
What happens when we start feeding these models their own output?
Ah, the synthetic data problem.
Exactly. If the internet becomes entirely flooded with AI-generated text and AI-generated images,
Yeah.
and then we scrape that exact same internet to train the next version of the model.
It is like making a photocopy of a photocopy of a photocopy. The quality degrades every time.
Does the blindfolded darts player actually get better? Or do they start hallucinating a dartboard that doesn't even exist?
That is the absolute bleeding edge frontier of research right now. It is called model collapse. If the input signal degrades into synthetic noise, the model's grip on reality starts to drift.
So as engineers, we might find that our most valuable asset in the near future is not our code or even our compute power.
It is going to be a verified, human-generated data set. Pure, organic, non-synthetic truth.
Organic data. I can see the premium tier pricing models already.
It will definitely cost you extra.
Just something to think about while you're debugging that race condition tonight. We will be back next time to dive even deeper into this.
We are going to look at neural networks specifically.
What actually happens inside those hidden layers. But for now, thanks for jumping into the deep dive with us.
Keep learning.